All right, compiler construction 9. So in the last class, we introduced the new language R2 that had control flow operations, the booleans and the if statements and the comparison functions. And so what we're going to do today is we're going to basically get about halfway from turning that language into x86 code. And to do that, we're going to talk about the changes that we're going to make to our C language and our X language. So first we're going to go from C0 to the C1 language. And C1 is going to be just like C0, except it's going to have a few things that are different. The set of arguments are going to be bigger. Arguments are going to include true and false. And there's going to be a new category of comparisons, which will be, equality, less than, or equal to, greater than or equal to, and greater than. There's going to be new expressions. So the expressions will have the things that it had before. It'll also have not, an argument, and it'll have a comparison of two arguments. Then there's going to be new tails. Remember that the tails before were either a return or a set. Now there's going to be a new one, which is going to be a goto of a label, and there's going to be a goto if of that's going to take two things. It's going to take a comparison between two args, and it's going to take two labels. The label to go to if it's true, and the label to go to if it's false. Now notice that this might be a little bit weird because a goto if is going to include a comparison. It's not going to include an argument. It will include a comparison operation itself. This has to do with the way that if statements are actually going to be compiled and represented in the x86 code. Now the interpreter for this is going to be pretty straightforward. So when we interpret a C program, obviously you know what's going to happen with a true or a false. We're going to just represent those as true and false. Same with comparisons, nots, and compares. Okay, these ones are the more interesting ones. So if we interp a goto of a label, all we're going to do there is we're just going to interp the tail where we look up. Remember, there's this thing. It's a mapping from labels to tails. I forget what we called it. Let's just call it big L for the label to tail mapping. We're just going to go look up inside of L what that label is. So we're just going to go switch to do a different tail. Then if we call interp C and we get an L and we have a goto if of a comparison between AL and AR, and then we have a label for the true side and a label for the false side. Then what we're going to do there is we're going to interp T of L label K, where label K is equal to label T if V, otherwise label false, where V is equal to the interpretation of the expression compare AL, AR. Okay, so we're just going to look at this expression, treat this thing as an expression, evaluate it, see if it's a true or a false, and choose the appropriate one. Okay, so that's our change to the C language. I'm gonna talk about the change to the X language next, so that we can have both of those in mind, so that we can sort of know what we're even going to be doing in all the different parts of the compiler, so we can sort of know where the destination is. Okay, 9.2. We're going to go from the X0 language to the X1 language. X1 is going to be very similar to before. So arguments are going to be extended. Remember, arguments used to be registers, variables, offsets, and concrete numbers. They're going to include one more thing, which we're going to call a byte register that has as an argument a register. Basically, what a byte register is a way of looking at just one component of a register. So we think about in a register like RAX, but RAX is really 64 bits. So this is 64 bits. So this one right here is 63, that one down there is 0. And this whole thing we label RAX when we look at the entire 64-bit quantity. But actually, if we split it at 31, then this part down here is labeled EAX. And then if we split it again at 16, really at 15, then this right here is just AX. And then if we split it at 8, really at 7, then this right here is AL, and this side is AH. So the idea here is this is the A lower, the A higher, the A extended is the entire 16-bit thing. The EAX, that is the extended A extended, that's the whole 16 quantity. And then the really big extension of A is all the 64-bit things. So basically what byte register byte reg is talking about this piece right here. That one is the byte register. So that is looking at this register as if it were a single byte. What's going on with this? Well, true and false are just numbers 0 and 1. And so we need a way to read off just that final little component, which we'll write as a byte reg. Okay. The next thing that we need is something called a comparison code. And a comparison code is either E for equality, L, which I'm writing as a curly loopy thing, so that you don't get it confused with the bars. So L for less than, LE for less than or equal to, G for greater than, and GE for greater than or equal to. Then we have new instructions. And so the new instructions that we need are called I can't read my notes. It is the XCRQ. Yes, okay. It is the exchange instruction. Oh, sorry. No, that's not what I want. It's not exchange. It's the XOR instruction. Sorry. Erase that. Okay, here we go. Okay, so we have the XOR Q instruction, which takes 2 args. We have the compare Q instruction, which takes 2 args. We have the set CC arg instruction. These A's are all args, by the way. Arg instruction. We have the move ZBQ instruction, which takes 2 args. And then we have the jump if CC label instruction. Okay. So, how does this work? So XOR Q is an XOR. We're going to use XOR to get not, because if we XOR something with with 1, then that's a not. Compare Q compares 2 things. Now here's kind of an interesting subtlety. In the C language, we always compare 2 arguments, and that compare means like you're doing a less than or greater than or something like that. But the way that x86 works is that when you do a comparison, you actually do all possible comparisons simultaneously. And after you do all possible comparisons, what you then do is then you read off from the flags which comparison you actually care about. And that's what set does. So set CC would allow us to actually compare a particular thing. So for instance, suppose that we wanted to do 5 less than 4, what that compiles to is that would compile to a compare q of 4, 5, and then a set L of AL. So what we're doing here is we do the comparison, and then we read off the L flag. Whoops. We do the comparison of 4 and 5, and then we do a set L on, we read off the L flag, and we set that into AL, which is this lower thing. The reason that we need these byte registers, by the way, is that this set operation cannot take as an argument RAX. It can only take these lower byte things. So yeah, so that's why we have to do that. Okay, so XOR does an XOR, compare and set allow us to do a comparison. Move ZBQ, so it's a move operation. So think of this as like a move Q, except that there's this ZB. What's the ZB going on? The ZB stands for we're moving a byte into a quad. So this right here is a byte. This whole big thing is a quad because it's one of these, 2 of these, 3 of them, 4 of them. That's why it's called a quad. So we're moving a byte into a quad because we're going to take that AL and we're going to move it into a register. Now what's the Z? The Z is that, well, if we move this thing, then where do these other bits come from? The Z says just make them 0. The other thing that you could do is you could do a move ABQ. And what a move ABQ would do is it would make all of the things have the same, all of the extra bits have the same sign as the the same value as the 7th bit. Which we would do if we were taking a 8-bit signed number and moving it into a 64-bit container. So that's ZBQ, and then jumpif, of course, does a jump. Now, printing out all these is very easy. The main difference with really printing them is that the main difference with really printing them is that when you do a set, you don't print a space right here. So like what I'm saying is that it wouldn't really be printed as set L. It would be printed as set L with no space. That's the way it would get printed. Similarly, a jumpif gets printed as the character jump, then the CC, and then a space, and then the label. So basically, the operations are like jump E, jump L, jump LE, jump G, and jump GE. Now here's another kind of subtlety about the jump if. The jump if says jump when this thing is true, not when it's not true. So really what you're doing is you're jumping over the false case. So if you think about how the labels work, immediately after the comparison operation, you're going to compare, then you're going to do an if, and then the thing after the if is the false case. And what the jump does is it jumps around the false case and goes down to the true case. We'll go over this again, you don't need to remember this. Okay, finally, let me comment a little bit about the rules of x86, and remember these rules are going to be enforced by patch. So compare Q cannot have a constant in the second spot. This is really weird and frustrating. Okay, so that means that it actually turns out that this spot right here, this 5, is not allowed to be a number. Now, the thing that's kind of nice about that is that you know that you'll never actually get 2 numbers in either of these spots, you'll only get 1. But what it means is that you may have to like flip the thing to the opposite. What I mean by flip it to the opposite, what I'm saying is that like, suppose that you wanted to do a less than, but you wanted to do a less than between A and 5. Well, that 5 can't be a number. So that means that you need to switch them. And now once you switch them, your less than now becomes a greater than or equal to. So inside of your code, you're going to have some logic there for making sure that you don't generate a comparison that has a constant in the second spot. It's really annoying, and this is the sort of thing that compilers have to deal with all the time. There's like these high-minded ideas about how am I going to do optimization and how am I going to structure my compiler, and then there's this low-level BS about the way that the assembler actually works. Another thing that's probably a little bit obvious is that move ZBQ also can't have that. And that's because the second position is the destination, so of course you can't move something into a number. So this argument right here is not really an argument, it has to be a destination. All right. Okay, so yeah, and what I've just talked about, you got to update your X interpreter to deal with all of that stuff. Now, and do I have any advice for how to do that? XOR you just implement, move ZBQ you just implement as well. Move ZBQ is essentially a no-op, by the way, if your language allows you. Probably what you'll do is you won't really have. What you'll really do is you'll just make it so a byte register is the same thing as the register. If you wanted to be super accurate, moving something into a byte register would get rid of all the top bits, but probably this won't matter. A jump if, is pretty straightforward. Really, the compare and the set is the thing that's most complicated. Basically, what's going to happen is that when you do a comparison, what it's going to do is you can kind of think of it like this. It changes a whole bunch of global variables to be the answer to all of the comparison questions. Imagine that your X interpreter has a variable called E, L, LE, G, and GE. So it has these 5 global variables, and when you do a comparison, it modifies those. And after modifying them, what set does is it reads from those things into the argument. And that, by the way, is really quite accurate. That's really how it works. The thing is that comparison modifies the flags register. And the flags register is basically this register of a whole bunch of individual, little pieces of information. And of course, we know that registers are global variables. Okay, so that's really what's going on. And set is like a move, except that it's moving from this special flags register to a byte argument. All right. Okay. So now we can start talking about how to really start updating the pieces of our compiler. So we have our new version of the C language, and we get to the new version of the C language by doing the RCO pass. So let's talk about how we need to change RCOs. Basically, RCO is going to have, remember, RCO has arguments, complex statements, and it has expressions. So here's the way we're going to do that. We're going to say that an RCO expression is going to be what it was before, except that also it could have an if statement with a comparison between an arg, and 2 e's. A complex, remember, complexes are the things that are on the right-hand side of lets. That could be a not of an A. It could be a comparison of 2 A's. Or it could be an if statement with a comparison of 2 A's and 2 E's. Now this right here is weird. Because remember, the whole point of RCO is to make it so that it's not recursive anymore. But of course, here is a place where it is recursive because a complex has an E inside of it. What's supposed to happen is that E's are only at the top. Think of it like this. This comparison right here is saying that are we going to run this rest of the program or that rest of the program? Because remember, E's are like tails. This one right here says, is this value going to take on, remember, is this variable going to take on this value or that value? And then finally, A's, they just also include true and false. Being, yeah, okay, that's fine. Okay, so we then need to update, the actual rules for RCO, and let me, yeah, I'll go into detail on this. Okay. So let's first look at a concrete example and then expand out all of the rules. Just trying to double check. We are in class 9. Okay, we got 10. Okay. Okay, so let's look at a concrete example of what RCO would do on a particular program. So here's the program. It'll be an addition of an if statement of a less than of read and 5, where if the if statement is, if that's true, then we'll return 17. Otherwise, we will add 8, 9, and 10, close the 9, close the 8, close the if statement. And then after that, if we'll do a plus of a read and 21. Okay. So now here's what this program is going to look like. It's going to look like this afterwards. And then we'll talk about, how we actually get this. We'll start off with a let of v0 equal to read. And this is the read that is the first read to happen. The first read to happen is that one, because it is we evaluate from left to right. Then what we're going to do is we're going to let v1 equal an if statement where we have a comparison of v0 and 5. That right there is our compare, because remember, ifs include a compare in them. The then case is going to be just 17. And the else case is going to be this thing right here. And that thing is going to be a let of v2 is going to equal 9 plus 10. And then there's going to be a v3 where we have 8 plus v2. And then we're going to return v3. Okay. Then we're going to have a let of v4. And v4 is now going to be this other side. So this is going to be another read. And so that's that read right there. Then we're going to have v5 is going to be v4 plus 21. And then let me push this down a little bit. Then we're going to have v6 equals v1, that's the left-hand side of the expression, plus v5, that's the right-hand side, and then we're going to return that v6. So this right here is going to be the result of this program. Okay. Notice that the way that our program looks is that we have a sequence of lets like before, except that the right-hand side might be a variable, might be an if statement. And if there's an if statement, then it will then be a sequence of lets and a sequence of lets. It's possible that we could have had a different program. Like, imagine that we had this if on the outside. If the if was on the outside, then like the left-hand side would be a sequence and the right-hand side would be a sequence. We call that tail position. Whether or not the if statement is in tail position, meaning that the result of the if is the thing that gets returned. That's very relevant to doing this process. So let's start writing down the algorithm. Okay, so RCOP is going to take a program and return a program. And so we call RCOP, and it'll get some program with some info we don't care about and some expression. And what we'll do is we will We don't have any info. And we're going to call RCOE with an empty environment. And we're going to give it true and E. Okay, now what are these things? RCOE, it takes as arguments row, which is the mapping from, it takes a mapping from variables x to e's, which we call row. It also takes a Boolean, which tells us whether or not this thing is in tail position. And of course, the program starts off being in tail position. Then we have the expression, and we're going to return an expression. Okay. Now, what we're going to do here is what we're going to return is the let star of the new variables and a, where the new variables and a is the result of calling RCOA with with row, tail, and E. Now let star, it takes a sequence. Let me just write a little note over here. Let star, it takes a list of pairs of a variable and an E, and it returns an E. Basically what it does is it just adds a let in. So for each one of these variables, it says let this equal that, let this equal that, let's equal that, until it gets to the final thing. We saw this before. It's the same thing from the older version of RCO. Okay, now RCOA, it takes a mapping from X to E, just like before. It takes a Boolean, just like before. It takes an E, and what it does is it returns one of these complicated things. It takes a list of pairs of variables and expressions, and it returns an expression. So these are the new variables that are needed to evaluate this thing. And this E right there is really an arg. And this E right here is really a C, a complex. Okay, so now let's work through the cases. So we call RCOA with row and tail. Okay, now what happens if we see a variable X? In that case, what we're going to do is we're going to return an empty list, which I'll write as empty, and then we're going to look up inside of row what it remaps X to. Because this mapping, by the way, it maps things to A's. A's are just a kind of expression. Okay, now what if, instead of a variable, what if we got a number? Well, in that case, we'll just return empty, and then that same number. What if we got a bool? Well, then we'll return empty and that bool, because these things are values, so they're already simplified. What if we got a read? If we got a read, then what we'll do is we'll return a list that contains a pair that has that new read variable, and it's bound to read. And then we'll return the read variable. Because a read is not an argument, so it can't be the thing that gets returned. Okay. What if instead of the read, we get a unary operation like not? So this is going to be the same. I'm going to write unary. So I'm going to write una. Okay. And so that is what we would do for a negation, for a subtraction, and any other unary operation that we eventually add. So it's going to take some argument, which we'll call EL. In that case, what we're going to do is we're going to have whatever the new variables are for L, and we're going to add to those a new variable for the unary operation, and we're going to add, and then that's going to be a unary operation and the argument for L, and then we're going to return whatever that new variable is, where the new variables for L and the argument for L is equal to calling RCOA on row and false, and then A. So this false is important because remember, that tells us whether or not the thing is in tail position. And this expression right here is not in tail position because it is the argument to a unary operation. So that's a big deal. A very subtle thing, but it's a big deal. Okay, now what if we have a binary operation? If we have a binary operation, then we have an EL and an ER, and it's going to be extremely similar to this. We're going to have all the things for the left, and then all the things for the right. And then we're going to have the new variable for the binary operation. We're going to have the binary operation itself with the AL and the AR. And then we're going to return the new binary variable, where the new variables for the left and the argument for the left equals RCOA of row false, the expression on the left, this right here was supposed to be expression on the left, and then the new variables on the right and the argument on the right equals RCOA of row with false and the expression on the right. Okay, so all we need left are lets and ifs and we'll be done. We'll do lets next. So suppose we have a let where we have x, xe, be. Then what do we do here? Well, here we're going to have the new variables for the x and the new variables for the body. And then we're going to have the argument for the body, where the new variables for the x and the argument for the x are calling RCOA on row and false, because this is not in tail position, on the xe. And then the new variables for the body and the argument for the body come from calling RCOA on row, where we extend it with a mapping from x to ax. And then here we pass in whatever tail was before, and then be. So that's not a true. It's whatever tail was before. So we got in tail as an argument, and it could have been true or false. So that means that this body expression right here, it has the same tailness as the whole expression does. All right, now let's switch pages and do the last rule, which is the most complicated rule, because it is the rule for conditionals, for if statements. Let's go back to the top. So this is 9.6. Okay, so what if we get called with RCOA and we get a row, a tail, and then we have an if statement that has the expression for the condition, the expression for the true, and the expression for the false. Now what we need to do is we need to return something that's kind of complicated. We need to do an if inside of our compiler. So I'm going to put it inside of a block. I'm going to write an if right here, and this is inside of our compiler. If this is in tail position, then we'll do one thing. Otherwise, we'll do something else. So if it's in tail position, then what we're going to do is we're going to return the new variables for the conditional, and we're going to return what we're going to call if prime. If prime. And then otherwise, and again, this is in a box, so that means it's inside of our compiler. Otherwise, what we're going to do is we're going to return the new variables for the conditional plus the if variable that has the if prime as its argument, and then the new if variable. Okay. Now, what are these things? So first what we do is we look at the conditional. And we're not going to call RCOA on it because we need more information. Because we need to make sure that this conditional right here is actually a comparison operation. If it's not a comparison operation, then we won't be able to turn it into, let me go all the way back here. If it's not a comparison operation, we won't be able to turn it into a goToIf because we won't know what the compare is, what kind of comparison we want to do. And if we don't have that as a compare, then we won't know what setC to do and what jumpIf to do. So we need to make sure that the actual conditional gets analyzed in a special way. And that's why this is complicated. So what we're going to do is we're going to call a totally new function that's going to be called RCOC, RCO for conditionals. And it's going to give us back the new variables for the conditional. It's going to say what comparison the conditional is, what argument is on its left, and what argument is on its right. And that's going to be the result of calling RCOC with row and EC. We don't need tail because we know it's not in tail position because we know it's a comparison. Now, what is if prime? If prime is equal to an if statement, and this is an if statement that's like the if in our language. So what I'm going to do is I'm going to write it as a capital if to make it clear that it's the one that it's like the data structure in our language. And it'll be whatever the comparison is with the argument on the left and the argument on the right, where its then side is calling RCOE. Remember, RCOE, that's the one that uses the let star. It's the one that captures all of these new variables and turns them into lets. Because remember, if the right-hand side of a variable is an if statement, then it needs to capture all of those lets. Okay, so this is the RCOE of calling it with row and whatever the tail position was before, and the expression that's the true expression. And then the other side of the if statement is the RCOE with the same row, the tail position, and the expression that's the false expression. All right, now what's RCOC? Let's look at that next. Line 7. RCOC, it takes that mapping that goes from X to E, where those E's, by the way, are A's. And it also takes an expression, and what it does is it returns the new variables, which is the same type as it was before. It returns the comparison operation, and it returns two arguments. The argument on the left and the argument on the right. Its whole purpose is to get down to a binary operation. So imagine that it gets down to, oh, by the way, we know that this program is type checked. So that means that this thing, this E right there, cannot be a number. And it can't be, it can't be a number. It can't be an addition. It can't be a unary subtraction. It has to be something that could possibly have the right type. So that means that it could be a comparison. So we'll say row and the comparison with the expression on the left and the expression on the right. In which case, what we're going to do is we're going to return the new variables on the left plus the new variables on the right, plus whatever the comparison operation is, the argument on the left and the argument on the right, where we call the new variables on the left and the argument on the left from doing RCOA on row false and the expression on the left, and the new variables on the right, the argument on the right, RCOA with false and the expression on the right. Okay, so that's one way that it could be. That's one thing it could be. It could be a comparison. The other thing it could be is it could just be a concrete value, right? So it could be an actual Boolean B. In which case, what we're going to do is we actually have to introduce a new variable. Oh, sorry. No, never mind. There's actually a simpler way to do that case. So we'll do that one next. Not next, but in 2. Okay, it could be a let. If it's a let, then that means that we have a let of an x, an xe, and a be. In this case, what we're going to do is we're going to return the new variables for the x plus the new variables for the body. We're going to return the operation that's inside of the body, the argument on the left, and the argument on the right, where the new variables for the x and the argument on the x is calling RCOA with row false and xe, and then the new variables for the body, the operation in the body, the argument on the left and the argument on the right are the result of calling RCOC, because this is inside of the conditional, with with row, where we have a mapping from x to the argument for x. And here we also know, there's no tail argument because it's RCO, and they're the body expression. Okay, and then finally, if we got anything else, we'll just write other here. What we'll do in that case is we're going to return whatever the new variables are. Then what we're going to do is we're going to return the equality comparison with true, which is an argument, and then a, where we have the new variables and the a as being what happens when you call RCOA with row false and whatever the other thing is. The idea here is that if we didn't get a comparison and we didn't get a let, then that means that we got something else, and that something else we're just gonna have to put in a comparison for true. So this is kind of like the case where it doesn't get optimized, it doesn't get turned into the concrete comparison. We basically did a comparison earlier that was used in multiple places, so it didn't get substituted, and then we then we can't generate the core if statement. Okay, so we now have our RCO pass done. And what we'll do next is we'll do the explicate control path, or the econ path. And what that one does is it takes R1 programs and turns them into C programs. Sorry, it takes R2 programs into C1 programs. So econ, right, it takes R into C. So here's the way it's going to work. Econ P of some program with info that we don't care about and a body expression is going to be equal to a program with no info, and it's going to have a label to tail prime mapping, where label to tail prime is equal to, actually, you know what, I called it L before when we were talking about the interpreter, so let's just call it L. Just call it capital L. So L prime, where L prime equals L, except with a mapping from body to T B, where L and TB equals calling econ E, and this is going to be kind of exciting, where econ E is going to take as an argument a lambda that takes the final argument and returns that final argument, and then is called with B. Okay, so what's going on here? So econ E, its type is that it takes a function that takes an argument and returns a C expression. It returns a C tail. So it takes a C argument and returns a C tail. And it takes an expression, that's an R expression. And what it does is it returns a label mapping, a label to tail, plus a tail. Okay. This is kind of deep what's going on here. This right here is like a static continuation. Remember the way that we talked about continuations in the organization of programming languages, where what they do is they encode what happens after something? Here what we're doing is our compiler is going to keep track of what happens after things inside of the program, but on its own. So now all this econ E thing needs to do is go through the RCOEs. So that means that it could get a final argument. Okay, so it could get, we could call econ E with K, and we could get back something that's boring. So like a boring thing would be like a variable X, or a number N, or a Boolean B. And whatever that thing is, what we'll do is we'll just return an empty mapping, and then we'll call K, and we'll give it econ A of that boring thing. So econ A is unchanged from before. It just turns a simple R argument into a C argument. So like it would turn a variable into a variable, a number into a number, a bool into a bool, etc. Okay, so that's the boring case. Now a case that's going to be familiar. So we call econ E and we give it a continuation. And what if we got a let that is a let of an X, an XE, and a BE, where that one right there is not an if. So it's not an if statement. In that case, what we're going to do is we're going to return L, where the tail, the thing that gets returned, is calling, we're going to have a sequence. Remember, sequence is the way of taking two tails and sequencing them, with a setbang of X and econ C of XE, close that, and then BT, where L and BT is a result of calling econ EK on BE. So this is just like before. So these two cases together are like what our old econ function was. But now we need to deal with what happens if we get an if statement, or if there's an if statement inside of that XE right there. So those are the complicated parts. So let's do the if first. So if we do econ E, where we have the continuation K, and then we have an if statement where there's the comparison, the argument on the left, the argument on the right, the ET, and the EF, what are we going to return? here's what we're going to do. We're going to return all of the labels that are on the T side, all of the labels that are on the false side, and then we're going to have one more label that we'll call new. And then what our tail is going to be is our tail is going to be a go-to if with the comparison of the argument on the left, the argument on the right, and then we're going to have the label for the true and the label for the false. All right, now where the new labels for the true side and the tail for the true side is the result of calling econ e k on the expression on the true side, the labels for the false side and the tail for the false side is calling econ e with k and ef. This al is really al prime and al are, and so al prime is just calling econ a on al, and ar prime is calling econ a on ar. That just like converts the data structures. Okay, now what is new? So new is a mapping that goes from the true label to the true tail, and from the false label to the false tail. Now these labels are newly generated labels that are unique in the program. Okay. So these are the easy cases. So this part of econ e is like it was before. This one basically just says if you get to a point where the tail splits between two different things, well, you can either go down one or the other. And so these basically correspond to situations where a program is either a straight flow, like this, okay, or where a program reaches a point where we could do one of two different things. Okay, so this is, so like, let's say right here, this is one right here. Sorry, it's off screen. So that's one. Those first two cases are one. And then this case right here is two. So this is the one situation, and this is the two situation. But there's another situation that's possible, which is that if our program starts off doing one thing, and then splits, but then has to come back to the same point. So that's going to be what's on the next page. That's when there is a let, where the right-hand side of the let is an if statement. Because we do something, and we hit the let binding, and then we have to do either the true side or the false side, and then come back. So that's what's next. So this is 9, 9. Okay, so that looks like the following. We have an econ e of k, where we have a let statement with an x, and then an if of a comparison of al, ar, the expression on the true side, the expression on the false side, and then that is all inside of eb. Okay, so that's the situation we're dealing with. And actually, I really don't like that it's on two lines. So let's move it over a little bit. Then we'll move this to here. All right, good. Okay. Okay, so what does this equal? Oh, and I don't like that I can't write the equal sign. So here's what we'll do. We'll erase this k. We'll write it closer. Then we'll move all this over. And we'll write the equal sign. Okay, good. Okay, so what does this equal? Here's the way that's going to work. we're going to have the labels for the true side. We're going to have the labels for the false side. We're going to have the labels for the body. And then we're going to have the new stuff. And now what we're going to do is we're going to have a goto if, where we have the comparison between the argument on the left prime, the argument on the right prime, the label for the true side, and the label for the false side. All right, all normal. Where the labels for the true side and the tail for the true side is econ E of the new continuation and ET. The labels for the tail, the labels for the false and the tail for the false is econ E of the new continuation and EF. The labels for the body and the tail for the body is econ E with the old continuation K and the expression for the body. Now, what exactly is new and what is the new continuation? So new is simple. So new is like this. So new simply has the label for the tail mapping to, the label for the true mapping for the tails for the true. The label for the false mapping to the tail for the false. And the label for the body mapping to the tail for the body. And now the exciting part, the new K. So the new K looks like this. It is going to be a lambda that takes whatever the final argument is, and what it does is it's going to return a sequence with a set of x to fa, and then a goto of the label for the body. And then we'll close that. All right. So now, what does that mean that our program is going to end up looking like? Remember we had this example program? Way back. Oops, no. Right here, this example program. So what is this example program going to turn into? Well, let's copy it. Let's copy it. Okay, we'll copy that. And then what we'll do is we'll go to here. Okay, move it in. Like this. Okay, and let's write down, what page are we on? Okay, we're on 910. Okay. So this program right here, what it's going to turn into is the following. I really want like more space. Okay, so here's what I'll do. We'll move this a little bit over. Whoops. Cancel. Don't do that. Okay. Okay, we'll move this to the inside. Okay. Okay, so here's what we're going to end up with. We're going to end up with the body. Am I writing? Yeah. Okay. We're going to end up with the body is going to go to a sequence of set v0 to read. Then, after that body, it's going to have a goto if of v0 less than v5 with label 1 and label 2. Okay, and then label 1, it's going to say sequence set v1 to be 17, and then it's going to have a goto label 3. And then label 2 is going to say sequence set v2 to be 9 plus 10. And then it's going to have another sequence. Let me erase that. Then it's going to have another sequence of set v3 equal to 8 plus v2. Then it's going to say sequence of set v1 equal to v3. And then it's going to have a goto of label 3. And then label 3 is going to be the rest of the program, which is going to be a sequence of set v4 to read, and then a sequence, of course, of set v5 to v4 plus 21, and then another sequence of set of v6 to v1 plus v5, and then a return of v6. And that right there is what our program turns into. Notice that this tail right here doesn't return, right? Instead, it just goes to either label 1 or label 2. And label 1 or label 2, they have to know that their job is to modify v1 and then go to label 3. And they have to share that. And that is the whole point, if we go back, that is the whole point of this k argument. The k argument, which we tell the t side and the false side what they're supposed to do with their result. They're supposed to set it to x and then go to a specific label. And if we go back and we look at the example right here when it's actually like a number, well, all we do is we call that k and we say, well, I don't know where this number is supposed to go. And so maybe it's the return from the final program, or maybe it has to be set to a particular variable, and then I'm supposed to go to some other place. So that's why we have this static compiler side continuation passing. All right, so that's the explicate control pass. And what we'll do next time is we'll start talking about the X sides of things. Yeah. Okay.